Hi everyone, and welcome to today's webinar, Systems Engineering to Go, presented by Zane Scott. My name is Donna Long, and I will be your host during today's webinar. As Vice President of Professional Services at Vitec, Zane manages the company's consulting and training organization. While Zane's path to system engineering is not conventional, he is not an engineer, but comes to the world of systems engineering with a background as a trial attorney, hostage crisis negotiator, labor management facilitator, and mediator. He has taught systems engineering methodology in a variety of settings. He delivered the SE 101 tutorial for the INCOSE International Symposium for 3 years, is a frequent blogger, and is co-author of Vitec's book, A Primer for Model-Based Systems Engineering. Together with Dave Walden of Sysnovation, he won a Best Paper Award at IS 2016. Before joining Vitec, Zane worked as a senior consultant and process analyst, assisting government and industry clients in implementing and managing organizational change. Active in the International Council on Systems Engineering, Zane is the co-chair of the Corporate Advisory Board and a member of the INCOSE Board of Directors. He is a member of the inaugural cohort of INCOSE's Institute for Technical Leadership and is particularly interested in developing leadership skills among engineers and other technical professionals. Before Zane gets started, I have just a few housekeeping items. We will be answering questions at the end of the webinar. Please send your questions in as soon as you think of them through the question tab on the webinar control panel. Zane will answer as many questions as he can today, but if we do not get to your question, we will reach out to you after the webinar. The webinar is being recorded. If you experience connection problems during the live presentation, a recording will be available within 1 business day. The recording will be published to Vitec's webinar archive, located on our website. At the conclusion of this webinar, a survey will open on your screen. Please take a moment to give us feedback on today's presentation or on what topics you'd like to see covered in future webinars. Now I'm going to turn the presentation over to Zane. Welcome.
Thanks, Donna, and welcome everybody. We appreciate your time and attention for the next few minutes. We're going to talk about a topic that I think is absolutely crucial. I fully believe that systems engineering is at an important juncture. We're at a juncture in terms of the shape of our market space and our profession as well. And so I'd like to spend a few minutes with you talking about some of the things that I see regarding that juncture. We're going to begin with a little bit of historical background. Systems engineering arose and was first identified as such at Bell Labs, and then through the 40s and 50s and into the 60s began to develop and to be recognized as a separate practice, if you will. The drivers for it were complexity and speed. The increasing complexity of problems and the solutions that needed to be applied to them were combined with a pace at which those solutions needed to be crafted, applied, revised, and reapplied. So we wound up with a situation where there had to be some way to get our minds and processes around both the pace and the complexity. For instance, the Semi-Automatic Ground Environment, or SAGE project, according to Lincoln Labs, consisted of a net of radars and other data sources, digital computers that receive the radar and other information to detect and track aircraft and process the track data to form a complete air situation, and to guide weapons to destroy enemy aircraft. So you, in that one system, had to combine the radar, the detection facilities, the missiles that would ultimately destroy the enemy aircraft, and consider the aircraft that were aloft in the system, identify friend and foe, a number of things, all of which had to be coordinated and controlled and worked into a net, into a system, increasingly using computers. Those kinds of projects begin to shape the world of systems engineering. And what developed from all of that was a situation where we had an increased pace, which actually came to be known in common parlance as a race. Particularly, we had a space race and an arms race. Sputnik went up and threw down the glove in terms of the space race, and President Kennedy spoke to the nation and said that we would put a person on the moon within the decade of the 60s. We were able to pull that off, but it was always a contest between us and the Russians as to who would get into space first and who would get into space in particular ways first. The arms race, on the other hand, fueled the strategy of mutually assured destruction and ranged from the development of the atomic bomb all the way up into stealth bombers. It too proceeded at the pace that had developed. Excuse me. Along with this, the profession began to expand its reach, and it did that by transferring the processes and principles of the profession from one application to another. So if you could make a missile to destroy an aircraft, then you could use some of the same processes to make missiles that launched us into space, to go through Gemini and Apollo, through Mercury, Gemini, and Apollo, into the space station and space shuttle programs. It expanded incrementally. If you could develop control systems for ships, then obviously you could also work with submarines. And so we made step-fashioned modifications from rockets into ships, into vehicles, into space, into submarines. And behind it all, increasingly, software became more and more and more important. And we expanded the reach of systems engineering by expanding from one application into another. However, this method of expansion and the market space that it was aimed toward began to create some issues and some problems for us. We actually baked into the whole notion of systems engineering a set of processes that were the foundation of our understanding of systems engineering. That continues to be true even to this day. When we talk about systems engineering, many, if not most, systems engineers will talk in terms of process. If you look at our systems engineering handbook, you'll easily recognize that it's very heavily process-oriented. It carries along the algorithms and heuristics that we use with those processes to do the business of solving problems with system designs. It was also very heavily product-oriented. So we began systems engineering in order to design missiles or ships or tanks or any of a number of products. And as we branched out, but we kept our product orientation. One of the examples of that is that when in COSI, decided to move into the world of healthcare, the first focus was healthcare devices. So if you could produce control systems for military devices, you could probably produce control systems for medical devices. And the product orientation was preserved. The product orientation began to shift and expand into the world of software. So not only could you develop the products themselves, but you could develop the software systems, the programs that controlled those products. All of those were incremental expansions. And the vocabulary was essentially preserved across those moves. So the product engineering, the software engineering had a shared common vocabulary, especially within product and within software. And that too transferred with systems engineering and with our understanding of systems engineering. One of the reasons why I say that we're at an important juncture is that there are some things going on in the world that are causing us to need to look outward. We need to look outward in terms of being able to solve new and different kinds of problems, and we need to look outward in terms of economic opportunity. So we're beginning to experience a change in the military market, for example. The battle space is changing. Stanley McChrystal wrote a very interesting book, Team of Teams, which discusses in some detail the kinds of changes that are occurring in the battle space and in the military sector. So you have those types of changes to which systems engineering is going to need to adapt. The economics of that space are changing. Today's probably a good day to talk about the criticality of this, since it looks like we're going to have yet another probably fairly short continuing resolution. Those many people say damage our military development, and certainly they damage the economic opportunity that's available in the world of systems engineering. As we try to expand, what we find is that if we expand by the practice, if we expand by looking incrementally at solutions that are similar to the ones that we have successfully applied to other problems, systems engineering becomes less extensible than it could be if we're able to look at theory and take a more extensible stance. We'll talk about that in a little more detail, and that's probably the major point that I'd like to make today, is that with this necessity to expand, to move to other problem sectors, to move to other market spaces, we need to have the most extensible understanding of our profession, of our discipline, and that's going to come to us through the theory and through the principles, as opposed to through the similarity of solutions. If you look at work that has been done by Terry Bayhill at Arizona, for example, Terry's got some very good discussions of the fact that you can map the concepts of systems engineering onto different conceptual frameworks. So for instance, the Plan, Do, Check, Act cycle, it maps very well to the systems dynamics that are set out by Peter Senge, for example, in the 5th discipline. They map to total quality management and Lean Six Sigma. They map to the kinds of things that Jack Welch did at General Electric. and even mapped to frameworks like the 7 Habits of Highly Successful People that Stephen Covey popularized. All of these mappings happen when we think at the level of concepts as opposed to applications. So when we think about schema, when we think about complexity, and we think about the ways that we think about problems, then we can begin to see some real extensibility. We need to look to our systems disciplines, the other disciplines, systems science, systems dynamics, for example, that think about systems. Look to the work of people like Henry Sillitoe talking about the connection between systems engineering and some of the other systems disciplines. The reason that this is so is that all of those disciplines are headed in the same direction and trying to do the same kinds of things that our discipline is trying to do. They're describing the same reality that houses the problems that we need to solve. So all of those things in terms of a schema and a way of thinking about the world are describing the same world. And therefore, it's really not surprising that as we work within those different frameworks, we begin to see similarities that emerge. Excuse me. There's an interesting example in some process modeling work that's been done and published in the Systems Engineering magazine. I've got the reference down here. Sarah Bonzo, David McLean, and Mark Avnet wrote a very interesting paper which was published in Systems Engineering called Process Modeling in the Operating Room, a socio-technical systems perspective. They applied a different kind of framework to what we would see if we stand back at the conceptual level as a systems engineering problem. It's very interesting. They use something called the design structure matrix. A design structure matrix, systems engineers could most conveniently think of as an n-squared diagram. In this particular instance, they took all of the process steps in order and arranged them in what is essentially for us an n-squared diagram, which was for them a matrix. And then they tracked the relationships, the process steps that depended on each other, process steps that, for instance, needed information from a previous step in order to complete a given step, process steps that had to be completed in order for a further process step to be completed. And they use the matrix to track that. So when you see the little ones, the little tick marks in the boxes, those mark the places where there are such relationships. That's the top left-hand box in that matrix. The bottom right-hand box in the matrix are all of the personnel that are involved in pulling off this process. The process that they mapped was what is called the perioperative process. It takes an operating room, an operating case that's going to be performed in the operating room, the patient, the room, the equipment. It prepares the room itself. It prepares the equipment trays, for example. It prepares the patient and then moves the patient into the operating room, goes through intubation and anesthesia, performs the surgery, extubates the patient, and ends when the patient is taken back out and the room is recycled for another procedure. So they tracked that and they looked at the dependencies for communication and interaction among the staff that perform this perioperative process and the interactions among and between the process steps. Then they combined them into the larger matrix that you see there on the left, which is known as a multi-domain matrix because it's both the staff and the process steps. We would see the process steps, of course, as the functional breakdown, and we would see the staff, in this case, the organization of the operating room, functioning as the components in this system. They put those together, and then they tracked the interaction of the staff with the process steps and vice versa, made the larger matrix. It was a great disciplined way to think about this problem, to think about the necessary interactions. They were discovering things in doing that. They were discovering that, for instance, transporting the patient from the pre-op into the operating room had not really been designated. There was not a staff interaction in particular situations. And so it was not anybody's particular responsibility to go get the patient. The person who was free at the moment that they were ready for the patient would go get the patient without an institutionalized way of communicating and making sure that happens in the most expeditious manner. So they were trying to look at the throughput in this system with the idea that you would put a bunch of these together, and so then you could begin to design an even more complex system for a hospital setting where there were, say, 10 operating rooms instead of one operating room. And how do you handle and what effects are there on the process of a number of scheduled operations in a number of operating suites with the full knowledge that you're also going to introduce emergencies which have to be done on the spot, and the schedule has to be rejuggled, and how does all of that have to happen? What they found was a really good way to track all of the interactions and relationships that had to be established and maintained in order to pull that off. But they made a very astute observation. I think one of the most important sentences in their paper: while the DSM, the Design Structure Matrix, provides a valuable tool for visualizing complex processes, it's actually not the most intuitive means of graphically displaying dependencies in a simpler system like this one. Nor, I would submit, in an even more complex system. The more complex the matrix gets, the less suitable it is. In terms of what this means practically, is that if you study the operating room process and then you go to the hospital administration and say, here, I'd like to show you what we've learned, and you put one of these multi-domain matrices up on the screen and start in, the first thing you have to do is a seminar on how to read the matrix. The process chart that they came up with, which I've got there on the right, is a more intuitive way to grasp and to explain to other people what's going on. What I discovered as I looked at this process was that I could take the information that they had garnered and instantiated into the matrix and put it into, in this case, our Genesis systems engineering tool, preserve all of those relationships, and then I could begin to portray that in a variety of different ways. So in this case, you have a functional flow block diagram enhanced to include information flow with information items and a trigger there in green, just by drawing on the information that they had gathered in the matrix. I could also, excuse me, take the staff that they had cataloged into that part of the matrix and arrange them into a component structure and a physical architecture. So you could begin to think about how you would perform the necessary functions in the most efficient way through a physical architecture. And we're doing systems engineering. So this becomes a way to handle systems engineering. But notice here that we're handling this process engineering using systems engineering in a way that we can also speak to the stakeholders and still preserve and use the information. If we make modifications to the information that we're portraying in this way, if we have a truly robust tool with a model behind the tool and we're drawing our illustrations from the models, then we can make a modification to the illustration, which is passed back into the model and preserved, and then affects every relevant view of the model that we might want to take. All of that done using the principles of systems engineering and model-based systems engineering. As we begin to think about venturing into other areas like hospital process re-engineering, we find that there are some impediments. One of the impediments is language, and that's the impediment that's discussed there with the views. So your portrayal of the perioperative process, for example, your illustration of it becomes a part of your language, a very important part of your language. And so you need a language, as those authors observed, you need a language that is clear and speaks to your stakeholders and the other folks that need to understand the process and the work that's going on. So language is a big impediment. There are other ways that language becomes an impediment. We tend to be a pretty insular community, and we go around thinking that we have shared assumptions about the meaning of language. One of these, as Donna mentioned, I'm not an engineer by background and certainly not a software engineer. So when I came to this world through the process improvement and the TQM orientation, I would meet with software developers who would say, our program is operating system agnostic. And that gave me some pause, because in the world that I came from, agnostic was an English word taken from the Greek. The Greek word gnosis means knowledge. Applying the prefix a to gnosis means without knowledge. So it puzzled me for a while, trying to figure out, why would software developers brag that their software was operating system agnostic? It had no clue, no knowledge. And yet all of the people who were using that term were understanding among themselves that operating system agnostic meant it didn't care what operating system was there. It would operate no matter what the operating system was. The program would work. That difference in language caused an impediment in translation from somebody who didn't come from that particular community. Our vocabulary works in the same way. Growing up in the mil-aero space, systems engineering is rife with acronyms. I kind of collect acronyms and initialisms. And the other day, I think I came across the ultimate. I came across the meta acronym. I was listening to a conversation in which the speakers were talking about TLAs. And just in case there's somebody on who doesn't know what a TLA is a three-letter acronym. So I think TLA is probably a meta acronym. It's an acronym about acronyms. So TLA describes acronyms like FBI. But we talk in acronyms, and if there's not an existing acronym, we'll make an acronym and throw those around. But if we go to a different area where those acronyms are not used, or even worse, they are used but used for something else, we cause problems. Billy Crystal in Analyze This plays a psychiatrist who's treating a mob boss, and the FBI calls on him. And the fellow from the FBI says, "Hi, I'm from the FBI, OCD." And Billy Crystal responds, "Obsessive compulsive disorder?" Because in his world, OCD means obsessive compulsive disorder. The agent, of course, responds, "No, organized crime division." Because in his world, that's what OCD means. So we have an impediment there, using vocabulary and language that's either not understood or is misunderstood by the worlds that we need and want to move into. So what's our path forward? How can we move forward? How can we expand our economic opportunity? How can we expand the impact of systems engineering? How can we move forward into the tomorrow of the profession? The first thing that we need to do is to not forget reproductive thinking. I'm not here today to say that incremental or reproductive thinking is a bad thing. It's a perfectly valid way of moving from one place to another. Looking at a solution and saying, you know, that worked here and I bet it would work there, is a perfectly valid exercise. It's just that we don't want to be limited to that exercise. Excuse me. We want to move into something that we call productive thinking. Now, in productive thinking, instead of looking at applications and moving from one application to another similar application, we ask ourselves, what are the principles behind the crafting of the solution in our experience? So what are the principles behind systems engineering? What enables us to apply those principles to problems? And then we need to ask ourselves, where else might we apply those principles? The easy and the glib answer is anywhere there's a system. Where are there systems? Literally everywhere. So there is systems engineering application nearly everywhere. What's the difference between systems engineering and most of its sister disciplines that think about these systems that are everywhere? The difference, I think, is that systems engineering is interventional. So where some disciplines look at systems, study them, try to understand their complexity, try to look at the system for the primary purpose of that understanding, as are different than our interventional system, where we're looking at systems that are involved in problems and systems that are involved in solutions to those problems. So we're seeking to intervene. We want to go a step beyond simple understanding to intervention. But if we think first about understanding the nature of systems and the nature of the problems and the nature of the complexity, then we can engage in productive thinking. How do we do that? Well, the first thing involved is curiosity and creativity. I've encountered folks who say, we don't want to associate creativity with engineering because engineering is based on science and facts and clearly defined principles, and creativity is too loosey-goosey. Number one, I would submit that without creativity, you don't have any engineering at all. So even the folks who advocate that line of thinking are ignoring the fact that they're creative or they wouldn't be successful. And secondly, we ignore the fact that creativity has been studied, that there are principles, there are best practices, and there are ways of understanding it. One of the things that we need to understand is that creativity is something that Albert Einstein called combinatorial play. Building on an idea from Pareto, Pareto said the first principle is that an idea is nothing more nor less than a new combination of old elements. Einstein said taking those elements, moving them around, and combining them in different ways, in other words, combinatorial play, is the heart of creativity. It's interesting, there's the story of Betty Naismith, and Betty Naismith was a secretary, I think, in Dallas, Texas, who worked in an office and then as a side job to earn more money, she painted signs on windows for businesses. Now, for those of us who are of a certain age here and remember a group called the Monkees, we might want to mention that Betty Naismith had a second job in order to support her son Mike, who was one of the Monkees, Mike Naismith, as in Mickey, Mike, Peter, and Dave. And that was before Mike made enough money to support both of them. But Betty began to realize at work that retyping and throwing away documents was hurting productivity. She knew that when she made a so-called mistake in painting an office window and in painting an advertisement on the window, what she very often did was obliterate the mistake by painting over it. So she began to experiment with different kinds of what was basically paint, so that if you mistype something in a document, you could go back and paint over it and obscure it and then type into the paint. And of course, what she came up with basically was what came to be known as whiteout. And she actually made a good deal of money as the inventor of whiteout. But that came across because she took elements that she was familiar with from her window painting job and made an application of those elements in her job as a secretary. That's combinatorial play. It's interesting, we could also argue that that is reproductive thinking, applying a solution from one place to another. But even the reproductive thinking depends upon creativity in order to see things. James Webb Young was an advertising executive who wrote a very interesting book. It's a little short book available on Amazon. It's available in a Kindle version. It's a very short and pithy read. It's called A Technique for Producing Ideas. And in that book, Webb lays out 5 steps for generating ideas. He says the first thing that you do if you want to generate an idea or solve a problem is that you gather up material. This can be done in the specific context of the problem, of course, but Webb recommends that we all be in the process of gathering material at all times. When we're reading articles that are arguably not related to anything that we're working on, when we're looking at the world, when we're out gathering up information, we're gathering material. We're performing the first step of Jung's process. The more material that we get, obviously, the more combinations we can make. So if you think of our minds as a jar of marbles, the more kinds of marbles that we've got in our jar, the more combinations we can make from those marbles. So the first step is to soak it up, to fill our jar. The second step is to digest it. And in order to digest the material, what we do is we take it out and we make combinations. There are numbers of interesting books on how we do that, how we engage in the creative process, how we make these combinations. Fascinating techniques. Some of them sound silly at first, but if you try them, you might be surprised at just how effective they are. But by experimenting around, digesting the material, learning what a given element can be combined with to create an interesting relationship, we're doing Jung's second step. Then he recommends that having thought about the problem and thought about potential solutions and potential combinations and dipped into our wealth of materials, that we just set it down and go away. That we move off and process unconsciously. He says that if we arm our minds with enough material and we play around with it regularly enough, then we can leave it to process material and combinations unconsciously. And that results very often in the aha moment of insight. Everybody's heard of the moment where you're in the shower and you have the idea. I had a colleague one time who said that he recommended that everybody keep a notebook in the shower. I've never really been able to come up with enough material and combinations to figure out how I could keep a notebook in the shower. But I have on occasion had some good ideas in the shower, and they really were kind of aha moments that came out of some background processing that I was doing. Generally, the aha moment is not well formed, and it's certainly not tailored. So the last step in Jung's process is to tailor that to reality. So if we can arm our minds with thinking about the fundamental concepts, the concepts of system, the concepts of complexity, and then the information from the world, and we certainly live in an information-rich world, then we position ourselves to do the thinking that's necessary for this creativity. One of the things that helps us is that our schema, the schema around which we build systems engineering, that we have requirements that drive behaviors, and we develop physical architectures or implementation systems that facilitate the behaviors that satisfy those requirements. That schema is not normative. In other words, we don't impose that on the world. That's the way the world works. It works that way when we guide it, and we hope that in doing our thinking about that schema and how we fit the problems and solutions into it that we improve the quality of our solutions. But it also happens by itself, if you will. So the schema positively describes reality. So if you decide that you want to buy something in particular, then the behavior is probably going to be coming up with the money to make that purchase, selecting the particular version of the purchase that you're going to buy, the model of the car, the particular model of the computer that you want, and then you're going to come up with an implementation structure, borrowing the money, using a credit card, robbing the liquor store, whatever it is that you decide as your means, your physical architecture for implementing the behavior that'll satisfy your requirements. Your requirements are there, and they do drive your behavior. In fact, one of the most interesting things that you can do with customers when it's appropriate and when you're in the investigative stages and studying problems is to look at their behaviors, and that generally will tell you something about what their requirements are. Very often in the process improvement world, we would discuss the behaviors that are actually going on and saying, look, based on these behaviors, we think these are the requirements that you're operating under. And the customer would say, well, no, I really don't want that. Okay, if you don't want that, then why are you performing a behavior that fulfills that? So if you stop the requirement, then you can stop or modify the behavior, which means that you can modify the architecture. All that's positive rather than normative. And systems engineering is set up to intervene in that. Now you might say, you didn't offer enough examples in other areas. You didn't show me how this would work in other areas. And that's true, and that's on purpose. Because if I show you other areas, then what I'm doing is encouraging reproductive thinking. Where can you take this thing called systems engineering? Where can it go? If I suggest to you 4 or 5 places to go, then what I'm doing is anchoring your thinking about how you move out. I much prefer to talk about this at the conceptual level, just as we want to think about systems engineering at the conceptual level, and then let you go. If you want examples, I recommend Nkosi's 2025 strategy book, A World in Motion. Take a look at that. There are a lot of interesting suggestions in there about problems that systems engineering could tackle and places that it could go. But I've intentionally been pretty lean on examples because I really do want to encourage us to get into that kind of productive thinking. Well, that's basically what I wanted to share with you today. If there are any questions, I'd be happy to take questions.
Yes, Zane, we do have some questions. The first question is from, I think you pronounce it Hasmik. I may be getting that wrong. But in your opinion, with the many worlds of language, due to the various professions, cultures, etc., how would a systems engineer best leverage such an impediment and turn it into an asset to solve an issue present in a complex system, i.e. methods, techniques?
Well, I think that's a great question. And I think there are a couple of don'ts. One of our tendencies is to tackle that problem by trying to standardize. And establishing standards, especially in the world of communication, can be helpful, but only to the extent that you standardize the communicators as well. So for instance, you see in the systems engineering world, you see the software engineering world advocating very heavily that we standardize the ways that we communicate. And if you look at their standards, they bear a very heavy resemblance to the communication that comes out of the software world. So we wind up with communications that are easily understood by people with an orientation to the software world, but not so easily understood by, say, a hospital administrator whose background for understanding process is total quality management. So one thing that we have to be careful of is we have to be careful of standardization. I think the thing that we do is that we have to be curious. The gather information gene that needs to be present for systems engineers is the gene that makes us want to go out there and learn. In order to understand and get the goodie out of the paper on the design structure matrices and their use in describing the perioperative process, really required me to do some learning and some thinking about what that language was. Once I gained an understanding of that language, then I could gain an understanding of how I would transfer concepts from my world into that world. So in essence, I was expanding my world. Just like learning foreign languages is probably the best way to expand our world, to broaden our world, and begin to understand culture. Learning the ways of communication in the other worlds that we want to move to is, I think, the critical step. So rather than saying, this is the standard, if you want to use systems engineering, you've got to understand this, you've got to speak this, we need to be the ones to take the initiative and branch out and try to understand.
Okay. I do want to encourage everybody, if you have a question, to go ahead and send me your question through the discussion panel. But the next question we have is from Jamie. How do we transition from application thinking to concept thinking?
I think the critical factor in making that transition is to first to simply ask ourselves, what are the principles and the characteristics of the problems that we are studying when we apply a particular application? So thinking about complexity and thinking about the ways that we deal with complexity, for instance, dealing with emergent behavior with respect to a particular type of problem, allows us to see what principles we're applying, and then we can turn to another problem area and say, okay, how could we apply those principles? So how is the concept of emergent behavior at work in this particular problem space? How is the system complexity? How is this problem space amenable or susceptible to the application of systems? So we simply need to move our thinking to the conceptual level, and then we can transition from simply transferring from application to application to transferring from conceptual framework to conceptual framework. And again, the other thing that's at work there is understanding the differences in the conceptual framework. So if you want to talk to total quality management folks about process reengineering, we need to learn our concepts well enough to explain them. Russell Ackoff said that you don't, if you can't express a concept in plain language that can be understood by any reasonably well-educated person, then you don't understand the concept. And so we have to develop our conceptual understanding to the point where we could explain it without falling into the pit of jargon and acronyms and special language.
Okay. We have one final question here. It says, can you say more about the schema being positive rather than normative?
Yes, as I pointed out, the schema describes a reality. Back in the beginning of my working with systems engineering and systems engineering tools and process design, Jim Long challenged me and said, okay, you're working with this stuff. Where else would you use it? Well, part of my background is in law enforcement and in solving and prosecuting crimes. And so I suggested to him that, excuse me, you could use the tools and methods of systems engineering to understand the system that was used to commit a crime. So in other words, they were trying to accomplish a set of purposes. They engaged in behaviors that were designed to fulfill those purposes, and they used an implementation structure. So they needed a getaway car. They had a requirement that they wanted to get away from the scene of the crime quickly. They needed a getaway car and didn't have one, so they had to have a behavior to steal a car so that they could have the car that became the component in their system. So I suggested to Jim that I could take everything that I knew about the crime and lay it out into the schema and see what was missing. And the things that were missing would then become the focus of an investigation. In other words, I need to know how this happened. I need to know where this came from. I need to know what they were trying to do and fill in the gaps. And once I had a complete understanding of the system, I'd have a pretty good understanding about the set of folks that might want to pull that off.
Okay. Hasmic replied with another good question, I think. So let's take this one.
Sure.
Many companies, corporations are undergoing major workforce transitions, baby boomers to millennials. What is your advice on how to best approach solving an SE-related problem when the properties, attributes of your team are on opposite extremes of the spectrum, so to speak?
I think that's a good thing because the same principle in terms of information and elements to put together. In other words, go back to our jar of marbles example. The more different kinds of marbles we have in the jar, the more different kinds of combinations we're able to create. So the more different possible solutions we can pull out of that jar. The same thing is true with people. In fact, I wrote a blog post, can't remember how long ago, maybe a year ago, about diversity. And the diversity in the outlook, whether that's a diversity in the outlook of people with different kinds of training, or the people who come as baby boomers versus the people who come as millennials, that diversity, if encouraged and focused on problem solving, can lend strength to the problem solving process of an organization. The thing that you can't do is like the thing that we can't do in systems engineering. We can't say, okay, the only systems engineering is systems engineering that expresses everything in terms of object-oriented concepts. Well, you just built a fence that fenced out all of the people who don't think in that way or know how to express those concepts in that way. So by reducing the ways in which you talk about something, you're reducing the ways, you're reducing the set of people that can understand you. Same is true in an organization. If we say, okay, we're going to set our organization up in a way that is run in the way that's convenient for baby boomers. And I'm a baby boomer. You know, I'm now in my 60s, so everybody ought to do things my way. You know, I'm close to the top of the organization, so I can enforce the processes down. But that's not true, and that's not the most productive way to proceed, because by insisting on a baby boomer design, I'm designing out a number of people with valid insights, different ways of approaching the problem. I'm fencing out solutions and narrowing my possible solution set. So I think the thing that organizations have to do is they have to figure out a way that millennials can be comfortable and baby boomers can be comfortable, and they can work together to craft solutions to problems without spending all their time pointing out that they think that their process is better than the other process.
Okay, thanks, Zane. That wraps up the final Q&A for today's presentation. I apologize if we didn't get to your question, but we will contact you directly to ensure it has been answered. If you have any other questions or comments for Zane, don't hesitate to send me an email. I'll forward it on to him. He would be happy to hear from you with any inquiries you have. Thank you so much for coming today. Our next webinar will be Streamlining Your SE Practice with Genesis 5.0 with Ron Kratzky. The link to register is on our website. Remember that at the conclusion of this webinar, a survey will open on your screen. Please take a moment to give us feedback on today's presentation or on what topics you'd like to see covered in future webinars. That's all for today. Once again, thank you for joining us and have a wonderful day.